So, good morning. Today we are going to continue on the topic semiconductors, but as you know, this course is essentially the devices and circuits. So the entire gamut of semiconductors, which forms part of a separate course, solid state devices or solid state physics, cannot be covered in in 3 classes. So it will be difficult. However, we ought to learn the essential basics that is required to appreciate the subjects that we are learning in this course, that is the devices and circuits. So for obvious reasons, because the fact that we are having all the devices, you take any device, it's all made up of semiconductors. And so virtually without semiconductors, you can't have these devices, you can't have these circuits. Today, modern day gadgets like computers or anything that uses IC, any electronic gadget, they use integrated circuits, and the basic unit, structural unit that makes these ICs to work, the integral circuits to work, is the semiconductors. So it's like a heart of a human being. Okay, with that introduction, I move on. So what we ought to know on semiconductors is the following. Number one, that what is an intrinsic semiconductor, what is an extrinsic semiconductor, and what are p-type and n-type semiconductors, how are they made, factors affecting the conductivity such as the concentration, mobility and the temperature, okay, and qualitatively and quantitatively we'll see that, because all the devices circuits, the essential thing is you ought to know what is the current voltage characteristic called the IV characteristic. Some people say CARA, current voltage CARA. And then you also ought to know for capacitance voltage for memory applications, because charge storage. So fundamentally, the carriers is the important attribute that is required. The carrier is the one that dominates. So what kind of charge carrier are there in semiconductors? We already know that it is electrons and holes. But how many holes per unit volume, how many electrons per unit volume depends on the doping. I introduced this concept, that's why I am telling you already. Now then, of course, when you want to excite an electron from the valence band to the conduction band, that is when only after excitation, if the electrons are available only in conduction band, then only we have the conductivity going, right? So what is the energy gap between the valence band and conduction band? Okay, so that will dictate the excitation level required for the electrons to come from the valence band or from the donor level to the conduction band. So that I will tell you what is donor level and acceptor level. Do not worry about it right now. So then how do you define a hole? What is a hole? We have already seen that a hole is nothing but a vacant state created in the valence band in an otherwise completely filled valence band. So I already told you that any material, for that matter, for example, the semiconductor at 0 Kelvin behaves perfectly as an insulator, because all the electrons are in their ground state, that is the valence state. Okay, so the states are filled. Now, when I heat the semiconductor, the electron goes to the conduction band by acquiring thermal energy, leaving that state in the valence band empty or unoccupied. So that is how a hole is created. So what we call the electron hole pair created due to thermal processes. Okay, so obviously in an intrinsic semiconductor, for every hole created, a vacant state created in the valence band, there is a electron in the conduction band. So the concentration of electrons and holes are equal. Okay, so that is the definition of hole. Then how does one estimate the carrier concentration? Okay, this is something which we have not discussed in the previous class. I will give you a very qualitative picture. Okay, so I will not get into the derivations and things of that nature, but the essential basics that you ought to know about it. So the carrier concentration is dependent on what is called Fermi-Dirac distribution function. The Fermi-Dirac distribution function happens because we have to invoke this distribution function because we are dealing with electrons which are subatomic. Now they are indistinguishable also, and they obey Pauli's exclusion principle in filling a state. So keeping these aspects in mind, the statistics that is to be applied is the Fermi-Dirac distribution function. What is the importance of this distribution function in the carrier concentration is something I will explain in detail in this class. Then moment I add a dopant to an intrinsic semiconductor, the conductivity is going to change. Obviously, because the dopant will bring either more holes or more electrons. So the carrier concentration is going to change. So what was the equilibrium carrier concentration in intrinsic semiconductor is not going to be the same in an extrinsic semiconductor. However, there is something called mass action law which will be obeyed both for an intrinsic semiconductor and an extrinsic semiconductor, which we'll talk about it. So what is this acceptor level? What is this donor level? Is something I will qualitatively explain so that you can appreciate this subject. Now finally, we'll also go about the quantitative expression for conductivity, okay, where I will bring the direct relationship with the concentration and mobility. Of course, the concentration itself is dependent on temperature. That is how it affects the conductivity. Okay, so we'll talk about that. In the last class, I did tell you that in a semiconductor, the conductivity increases with increasing temperature. Okay, which is, you know, not unexpected given the fact that as you heat the semiconductor, there will be a excitation of electron from the valence band released from the valence band, and it goes to the conduction band, readily available for electrical conduction. So what is an intrinsic semiconductor? Just I will give you an intrinsic semiconductor is one, okay, which actually, so this is the box diagram. So here my valence band, which is at the lower energy state, the energy is increasing in this fashion. This is my conduction band, and I will not talk about the levels which is within this. So this energy gap is the forbidden region where you cannot find an electron because there are no available states within this. So the states, when they are discrete in nature because of the quantum mechanics, consequence of quantum mechanics, you have a energy gap where there are no available states, although there could be a value of the probability function for the states to be occupied, but because there are no states, you cannot find an electron within this. Okay, of course, this is the case with the intrinsic semiconductor. However, if you have a defect state or due to dopant some states are present, then you can find electron. Okay, we'll come to that. So right now we are talking about intrinsic semiconductor, which means a semiconductor free of defects and does not have any impurity whatsoever. Obviously, at the intrinsic means coming from within, and at t equal to 0, the valence band is completely filled and the conduction band is completely empty. The intrinsic semiconductor behaves like at t equal to 0 Kelvin. The intrinsic semiconductor I will write it as SC, stands for semiconductor. So let me abbreviate it. Acronym is SC. Semiconductor, intrinsic semiconductor behaves like an insulator. Okay, the reason is very clear, because all the states remain their ground state, which is the valence band. Okay, so how do I excite it? So what I do is I apply thermal energy, so heat. So it is called thermal excitation. So an electron hops to this band over here. So it occupies here. Okay, and similarly another electron can occupy. Of course, it depends on the energy. It's a statistical process. So for every electron that hops, there is a vacant state. So created. So this electron I denote like this: hole, positive. So hole, because of the absence, there is a positive charge. Now you must remember. So this was earlier it was filled. Now because of the supply of heat energy, the electron has hopped. So a hole is nothing but a charge carrier created in the valence band as a result of an excitation of electron to the conduction band through the application of heat. So you can clearly see the very important thing is hole positively charged because of the absence of the state, positively charged, okay, and present only in valence band. Now present only in valence band. Now you must remember that the conductivity is current flow in a semiconductor is due to the motion of charges. Here the charges are of two kinds. So both the electron motion and the hole motion will constitute the total current. Okay, up to this level you understand right now. Good enough. So what is an extrinsic semiconductor? By extrinsic semiconductor we are adding impurities to the intrinsic material. When we add impurities to the extrinsic thing, what we do is we actually alter the concentration of electrons and holes. Now, one thing that I ought to have told you is here that in an intrinsic semiconductor, there is also, it is characterized by, okay, just a minute. It is characterized by, I have already told you, N0 represents the equilibrium electron concentration and likewise I will say that P0 represents the P0 represents the, let me see where I am. Okay, here. P0 represents the equilibrium hole concentration. So because EHPs are generated in an intrinsic semiconductor, it is evident that this is no rocket science. It is very clearly evident that N naught, okay, N naught equal to P naught. And N naught P naught will be equal to, this is what is called the mass action law. We will talk about it. Ni square, where Ni is intrinsic carrier concentration, and obviously different materials will have different Ni value, and it is dependent on thermal process. Therefore, when somebody says Ni equal to this much number, they must also tell what is at what temperature. Is that clear? Now, let us go further. On the extrinsic semiconductor material, the N naught obviously is not equal to, extrinsic semiconductor is one where you have altered the conductivity of the material by addition of small amount of impurities. Because we are adding only extremely small amounts, we call the impurity as what is called dopant. Impurity is called dopant because of the addition of extremely small amounts. Only you add. That's enough. Okay, so you can look at it. It's like cooking, sweet pongal at home. Okay, it is full of jaggery and rice and dal. Okay, now all you need to do is add very even one seed of cardamom. Okay, you give a flavor. Okay, that is what it is. So intrinsic semiconductor is there. You add extremely very small amount of impurity. The conductivity tailoring or the tunability in the conductivity is awesome. Okay, so that is the metaphor I will bring in. So you can remember that we are adding only extremely small impurities. When small impurities such as you can see in this diagram, antimony, phosphorus and arsenic, when they are added, they are fifth group element. We know that. And here you can see this is my what is called the EC, this is called the, of course, you have to understand this is called the EV for silicon because we are talking about silicon. Now, when I am trying to add boron, the boron level is close to the valence band edge of the silicon by an energy of 0.045 electron volt. Similarly, aluminum is close to this level and gallium is close to this level. So these are what are known as the acceptor energy levels. Because they are third group element, which means they have to get stable configuration, they need one electron so that it will come to octet. Now similarly here, the antimony, phosphorus, arsenic, they are fifth group element. They bring in the additional electron because they are fifth group element. They have 5 electrons in the valence, their valence shell, and 4 electrons will participate in the bonding. 1 electron will remain free, which means they are bringing extra electron. So obviously, the addition of extra electron due to each antimony atom or phosphorus atom or arsenic atom will bring, because they are willing to donate that electron. So obviously these levels are what is known as donor levels. It is a very simple explanation that will make it clear. Donor levels. Okay, so donor levels. So when depending on whether you are doping with fifth group element or third group element, you are actually injecting either more holes into the material in case of group 3 element. When you add the fifth group element, you are injecting more electrons. by virtue of that one extra electron which is not participating in the bond formation, covalent bond formation, being free. And because you can easily think like this, why these levels are close to the conduction band and valence band edge. Now let us talk about let us talk about n-type material. So in n-type material at 0 Kelvin, you can see that, okay, let me first explain why the donor level is close to the conduction band edge. It is very, very simple. You can think like this. Suppose, okay, suppose I am actually very rich, okay, and somebody needs money. All I need is very small excitation for me to think that I need to help someone. Because I have extra money in my hand, I just give it quickly. So that small energy is only required. Now he is actually getting the free money, so he is able to fly around. The conductivity is happening in semiconductor because of this kind of stuff. It's a metaphor, you can think like this, easy to remember. So you can easily think that this gentleman needs money, but I am having excess money. Definitely, when I am close to him, okay, when I am and he is in my vicinity, small excitation only required for me to immediately give the money. Okay, so he is like close kith of me, that I am close to him. Very similarly, when I am being added in silicon, and because I am already added in silicon, but I have an extra electron, all I need is very small heat energy for that extra electron to go up to the conduction band and the conductivity is happening. So therefore, I am willing to donate. The phosphorus is willing to donate the electron to the conduction band in the silicon. Therefore, the donor level must be closer to the conduction band in silicon. Similarly, when we talk about the p-type material, when boron or gallium or aluminum is added to the silicon, boron has 3 valence electrons. One state for it to get more, one state is empty as far as the silicon valency is 4. Silicon forms 3 covalent bonds with 3 boron, 3 other silicon atom. But it sees a boron now, and boron does not have electron to give. Rather, there is a empty state in relation to the stable configuration. So, which means boron readily accepts an electron coming from silicon, therefore it is an acceptor. So, 5th group element is a donor, 3rd group element is an acceptor, and these levels obviously have to be either close to the, in case of donor level, it has to be close to the conduction band. In case of acceptor level, it has to be close to the valence band. I hope this is clear. Let us move on. So how do we increase the conductivity by temperature? It is very, very simple. It has to, as the temperature increases, the concentration of free electrons and holes increases exponentially. Therefore, you will expect a behavior of the conductivity. Intrinsic concentration increases. So obviously, the you will have the conductivity also increasing exponentially. Okay, so it is very, very simple. Okay. So this is how you can see. For example, if you take about silicon, the intrinsic carrier concentration at T equal to 300 Kelvin, it is somewhere around 5 into 10 power 10. Okay, that will be at the room temperature, 5 into 10 power 10. Whereas when I increase the temperature, I am going to generate more thermal carriers. Therefore, I will have a higher carrier concentration. So obviously, conductivity is expected to increase. We'll see an expression for it. So factors affecting conductivity, one is the temperature, the other is the dopant. Okay, so these are self-explanatory, which we have already discussed in the class. So as you apply more heat, you are able to generate more electrons hopping to the conduction band. Therefore, you are going to have more charge carriers. So this is how temperature affects the carrier concentration. Now, another way to increase the number of charge carriers is to add the dopant. Obviously, when you add doping happens by a process called ion implantation. That is actually part of the device course, not within the scope of the syllabus. Okay, so there is a third year elective which is offered in the department. If you are interested to know more about semiconductors, opt for that course. Semiconductors are typically doped with elements such as boron, arsenic, phosphorus to change the and enhance their electrical properties. That is the beauty of semiconductor. See, insulator only is purely insulator. Conductivity cannot change. Metal conductivity is ultimate. You cannot alter the conductivity. But when you want to play around, you need that freedom to play around. The freedom to play around comes from the temperature and the dopant. When you do the temperature and dopant, you are increasing the carrier concentration in different means, by different means. Therefore, you are altering the conductivity. Essentially, you can actually tailor make a device as per the need. Okay, so that is essentially the thing. When you make a PN junction, you need to know what is a P-type material and N-type material in a device. Therefore, that is why we are learning this. Now, one thing that I must tell you. Okay, when I try to, thermally excite an electron, the electron has to go and occupy a state in the conduction band. So, does it occupy or not? For example, if I have a coin, when I toss it, the probability of getting tails and heads is equal. Okay, so because there are only two sides to the coin, so equal probability. Here, which electron hops and occupies and how many electrons occupy the states. So there is something called a distribution function. We have to apply statistical distribution function. Electrons being indistinguishable and they obey the duality and also Pauli's exclusion principle, which states that no two electrons can occupy the same state. So therefore, Fermi-Dirac came up with this distribution function. Okay, and this distribution function can actually help us in estimating the carrier concentration. I will show you qualitatively and directly get into the expression and explain qualitatively the carrier concentration. Now, let us think for this minute of this distribution function. How does it vary with temperature and with that is what and the energy. So, look at it here and how do I define Fermi energy? Okay, that is very important. What is this Fermi energy? So, this distribution function is nothing but what it gives is the probability that a state with energy E being filled by an electron. Okay, at a temperature, absolute temperature T. Okay, so that is the definition of the distribution function. The mathematical expression is like this. Now, I am not even bringing in the degeneracy factor and all those things. Okay, so for now, the very generic expression for Fermi-Dirac distribution function is 1 by 1 plus exponential of E minus EF in the numerator divided by KT. So this expression is for this exponential term. Now, when E equal to EF, that is when the energy of an electron is equal to the Fermi energy, okay, this numerator within the exponential term is 0 and because it is E equal to EF, you can actually see that it will become 0. 0 by anything will be 0. Exponential of 0 will be 1. So 1 by 1 plus 1, 1. So 1 by 2. So at E equal to, so you can define the Fermi energy as that energy at which there is equal probability of finding an electron or because it is off. Okay, so when it is filled, it is the maximum is half. So there is equal probability because the probability can take a maximum value of 1 only. So that energy level where there is an equal probability of finding an electron or not finding an electron. Not finding an electron means the level being unoccupied. Now I just want to tell you within the band gap. Within the band gap, look at this picture. Within this band gap, there could be a value for the Fermi-Dirac distribution function. But if there are no levels for the electron to occupy, then you want the probability of finding an electron, though will be according to Fermi-Dirac distribution function is there, but the electron concentration, electron will not be there because there are no available states. So probability function can have value, but you cannot find electrons here because there are no available states. Okay, this is a forbidden region, which means a region where you cannot find an electron. Okay, so that comes from the solving the periodic potential function. You can generate what is called energy wave vector diagram, EK diagram, and you get that. So we are not digressing too much. So enough to know that the energy level at which the probability of occupation probability is same as the unoccupation probability. That is the at absolute Kelvin. So you can see clearly at t equal to 0. Okay, at t equal to 0. Let us see, there are three curves which I will tell you each of these curves. So let us first follow the trace which is by the rectangular trace. Now at t equal to 0, I already told you there is an equal probability of finding or not finding. The probability function can take maximum value of 1. Okay, so at t equal to 0, you look at this expression here. There can be two conditions, either E greater than EF or E less than EF. When E is greater than EF and at t equal to 0, this is a positive quantity, and think about it, this is a positive quantity, and therefore exponential of infinity. Okay, and exponential of infinity. Okay, when E is greater than 0. What is exponential of infinity? It will become infinity. Therefore, 1 by infinity will be 0. So f of E for all energy states above EF at t equal to 0, they will not be occupied. Okay, think about it. At all states above EF, which means this region, the probability of finding an electron or the probability distribution function will become 0. Because it is 1 by infinity, 1 by infinity is 0. Now, for all energies less than EF, look at this expression again. This becomes exponential minus infinity, which means minus infinity means it becomes 1 by exponential infinity. 1 by infinity will be here. What will be 1 by infinity? It will be 0, which means 1 by 1. So f of E will become 1. So you can see at E less than EF. So this is T equal to 0 Kelvin. So don't get confused. This is T equal to 0 Kelvin. This is a condition. So we are only following the rectangular trace here, not any other trace at E. So if you see here at E less than EF, E will have f of E will be equal to 1. That is what this trace is up to here. See my path here. So this is the trace. So the probability function remains the same. And at that's what this rectangular trace is at t equal to 0 Kelvin. And any level above E greater than EF, E greater than EF, f of E will become 0. That is this. Now you look at this Fermi energy over here. This energy at this energy, you can see at E equal to EF, it will become, this function goes like this. Okay, so you can see here what you need to do is, now when I increase the temperature, the probability of finding an electron in the conduction band is more. Okay, so obviously when I increase the temperature, more states are going to be getting filled. Okay, so when I increase, let us say talk about T equal to 1. So more energy states above EF will be filled because of the hopping of the electron to the conduction band, they will be occupied. Therefore, it is no more 0 at E greater than or EF. But okay, at you have to think like that. Okay, so it is very evident that this level trace will become like this. But what is the probability of that being unoccupied? Because some of the electrons have gone to the conduction band. Therefore, the states, those states will be empty. Therefore, you will not get equal value of 1. You will get a reduced value, okay, of f of E for energies less than EF. Now, what is very important? This traces, what you see here, is actually symmetric about the midpoint. That's a beauty. So a state delta E above EF is filled is f of E plus delta E. State delta E EF is 1 minus f of E is empty. Below is okay 1 minus f of E. So that will be the okay. State delta E EF is not filled actually. Below EF. Okay, it is not filled because we are talking about f of E as the probability of filling. So 1 minus f of E will correspond to probability of not filling. Okay, so you can actually do this mathematics. You will see that the both will remain the same. So whatever value here, it will find an identical symmetry between this function. So it is symmetric with the midpoint Fermi energy. Okay. So what is very important, as I told you, if there is no available state at E within the gap, there is no possibility of finding an electron there. This you have to keep in mind. So I think that is good enough for you to understand. Definitely in an intrinsic semiconductor, because you are creating electron and hole pair. So N naught equal to P naught, which means EF must lie at the middle of the band gap. It's very simple. Okay, so look at these three diagrams here. Where does the Fermi level lie? So obviously, when you have an N-type semiconductor, you are bringing a donor level, which can, so more electrons will be there. So the probability of finding an electron in the conduction band will be more. Obviously, the EF should be closer to the conduction band. Similarly, in a P-type material, the EF must be closer to the valence band because the EF is corresponding to the probability of finding an electron. In an intrinsic, it is at the midpoint, definitely, because we are having more acceptor state, which means there will be more possibility of empty states over here because it is readily accepted the electron. Therefore, here the EF will be closer to the valence band edge. So you try to understand qualitatively, this is good enough. The quantitative expressions are there. I am not going to get in there. Now this I told you, if in the last class, see there is a one is called the probability of distribution function, other is called energy state. It is like occupation probability. In a bus there are 60 seats. Okay, so probability of a seat being filled, that is very important, and how many seats are also there, both are important. So the product of both will give you, okay, how many what is the concentration per unit volume. Same thing here, you have a probability of filling a state at E equal to at energy state E, and you have to multiply how many states are available. As I told you, within an energy level, there are countless number of states. Okay, to give you an idea about this density of states, it will be typically of the order of at room temperature. It could be anywhere between 10 power 16 and 10 power 19, depending on whether it is an intrinsic semiconductor or and at the temperature also, depending on the temperature. Okay, so so you have to understand that N of E, density of states, is very important, and the product of both, which is there are states, but whether those states are filled, what is the probability of filling when I get the semiconductor? So the product of both integrated over the energy level will give the concentration of electrons. Likewise, you will see the concentration of holes. The hole is a vacant state in an otherwise filled state in the valence band. So definitely equilibrium carrier concentration P naught will be equal to, I'll come to the limits. So the probability of the state not being filled will be 1 minus f of E. You multiply with density of states, and definitely here you can see the energy is increasing this manner. So this is my EV, this is my EC. The conduction band is at a higher energy and the energy is increasing like this. So there are lot of states here. I can draw only to the resolution permitted here. Lot of states. But the gaps which I have drawn is magnified. You have to think, you have to imagine a number, typical values like 10 power 16 to 10 power 19 per centimeter cube. These many states could be there. Typical values. Okay. Similarly, here lot of states are there. Now, I already told you, you must remember very important. When I excite an electron from the valence band to the conduction band, okay, the probability of finding an electron closer to the conduction band edge will be more. Okay. Similarly, the probability of finding an electron, okay, just a minute. The probability of finding an electron closer to the conduction band is more. The probability of the state being unoccupied near the valence band is more. So the distribution function, if you are to see here, you look at here, this is my distribution function. This trace over here. Now, far from the conduction band edge, okay, far from the conduction band edge, it is tending to 0. Far from the valence band edge, it is tending to 0. Okay, so you have to think like that. Okay, we have to look at, and this is 1. So 1 minus f of E will be 0. Okay, so when we talk about the probability of a state being unoccupied, this is the value of f of E. So don't get confused here. And this value of f of E. F of E gives the probability of finding an electron in a state, or probability of the state at E being filled. But 1 minus f of E will be probability of that state being unoccupied, empty. So when you take 1 minus of 1 minus 1, it will be 0. So if I integrate over the limits of, so if I integrate from, so here you integrate from EC, which is the lower energy level, all the way to infinity. The function, when I talk about the, let us talk about the intrinsic semiconductor, for example, the function, if you see here, it will be, it goes like this. F of E goes like this. It goes like this. You saw that. So this is my intrinsic semiconductor, for example, it will be at the midpoint. But if it is an extrinsic, it will be here. If it is this thing, it will be P type, it will be here. N type, it will be here. F of E equal to. But for an intrinsic semiconductor, it will be at the midpoint, close to the mid gap. So this is for an intrinsic semiconductor. EFI, I call it EFI to make it very clear. The I stands for the intrinsic. But if it is a N type, it will be here. And if it is a P type, it will be here. Now, if you see here, what I wanted to do, why I took infinity, because the probability function is anyway 0. So if I integrate above a certain energy level, because this is a product, if it is 0, the whole thing will vanish. So there is no harm in integrating with infinity. Similarly, I can integrate for the valence band, likewise minus infinity. But here the lower energy is minus infinity, because the energy is increasing in this fashion. So the lowest energy is minus infinity, the highest energy filled band is EV. So I have to integrate like this. When I integrate, I get an expression in this fashion. N naught equal to Nc exponential of minus Ec minus Ef. So the difference in the energy level, Ec, how much is the difference between Fermi energy and conduction band? That will decide how many electrons are able to hop in the conduction band. Similarly, the difference in the valence band and the Fermi energy in a p-type will decide how many holes are being created in the valence band. So you have to understand very clearly. So the expression, we arrive at this derivation, and here Nc and Nv are called what is called not merely, these are called effective density of states. So I introduce a new term called effective density because not all of the states are getting filled. So we will have only those states which matter to us. So we bring the term effective. There are plenty of states available, but not all of those states are participating in the conduction process. Therefore, we bring in this term, and at a given temperature, you have what is called, it is going to be constant. So when people talk about effective density of semiconductor, we also talk about, it is, you can see, I will give you some gist of this. There is a term called Mn star, there is something called Mp star. What does the star means? The star means, okay, Mn star. What is Mn star? Okay, so Mn star means, okay, this is not there. Mn star means effective mass of an electron. It is not rest mass because the electron is moving through the crystal. So effective mass of an electron, it has to move against the crystal field. Okay, there is a periodic potential because all the atoms are packed in a solid, and there is a potential function associated with this. Because of the, by virtue of quantum mechanics, you can actually see that, and because these electrons are moving through the crystal, they move under the influence of crystal field. Therefore, the mass will be different than the rest mass. Okay, so we are not right now, you take it like that because I'm not getting there. It is another class altogether. And Mp star is the effective mass of a hole. I told you the mass of a hole, rest mass of a hole is 0, but there is a effective mass of hole. There is a value, effective mass of hole, and different material, different periodic potential function. Therefore, the effective masses of electron and hole be different for different materials. Okay, and it is a direct implication of the temperature directly to the power 3/2. Therefore, the density of states will increase with the temperature. So the concentration will also increase. The conductivity also will increase. Qualitatively, this is good enough. You have to understand the concentration increases, that much is enough. Now, when I multiply N0 and P0, I will get like this. You will see the term EF getting cancelled out, and therefore you will get minus Eg by Kt. Now you think about it, at a given temperature, all the terms will be constant at a given temperature. So the product of N0 and P0 is a constant. Okay. Similarly, in an intrinsic semiconductor, N0 will be equal to P0. Therefore, there also it will be constant because we bring in the intrinsic energy level, Fermi level, it gets cancelled out, you get the same thing. So the expressions remain the same. This is what is called the mass action law, N0 P0 equal to Ni square. This is very, very important. What does that tell you? It tells you, if I know the intrinsic carrier concentration for a semiconductor, given semiconductor, and if I know what is the equilibrium carrier concentration of electrons, I can find the hole concentration. Likewise, I can find the electron concentration if I know the hole concentration. Okay. Now I come to the last point, which is the conductivity. Conductivity, when you talk about conductivity, the conductivity, we will see, I can actually show you the derivation. The electrical conductivity sigma equal to nq mu, how it came, Where sigma is the electrical conductivity, it is mho centimeter inverse. Okay, simply we also tell in terms of what is called Siemens per centimeter in case of a semiconductor device. Okay, or Siemens per meter in case of a bulk material. Okay, now where n is the carrier, number of charge carriers. In case of semiconductors, it is both electron and holes is going to give rise to the conductivity. Therefore, and the mobility of the hole is going to be different from the mobility of the electron, because their masses or effective masses are different, and they will definitely, because they will have to experience a different acceleration. Therefore, the mobility is nothing but is a parameter that measures how will a charge carriers move through a semiconductor under the influence of external field. Okay, so the charge carrier here are both electrons and holes. The electrons and holes move differently under the influence of field. Therefore, you have a separate value for mobility of electrons, mobility of holes. Therefore, you get this kind of expression. In case of intrinsic semiconductor, the number of holes is equal to the number of electrons, because it is all excited thermally. Therefore, you will get an expression like this. So you can simply see through this expression that for an extrinsic semiconductor, N naught P naught equal to Ni square, and the in case of N-type semiconductor, the majority carrier is the electrons. Therefore, the conductivity will be dominated by electron. In case of P-type semiconductor, the majority carrier is the hole. The conductivity will be dominated by the holes. So, with that, you can also see the value of the mobility over here. So, mobility, you can actually see the unit measured is mu n equal to 0.135 meter square per volt second. Those of you who are interested, I can show you the derivation, but for now it is enough to understand sigma is given by the expression nq mu. Okay, product of where n is the number of carrier, q is the charge that each carrier. So you multiply, you get the total charge, and where mu is the mobility, you multiply the mobility, the conductivity is given. The unit is either you write in terms of ohm centimeter inverse, or you write Siemens per centimeter. Now you can see the carrier, typical carrier concentration. So as I told you, in case of N-type, the conductivity is dominated by electrons, and this is illustrated in this example. Let us look at here. For example, silicon intrinsic carrier concentration is 1.5 at 300 Kelvin. I have to specify this temperature, as I told you. Okay, because the density of states is a function of temperature, which will vary. Effectively, N naught will vary. Similarly, P naught will vary. Therefore, I need to specify at what temperature I am talking about Na. So, extrinsic semiconductor with arsenic, I am doping with 10 power 21 atoms, which means it is really heavily doped. And each atom contributes to 1 electron. So, I am going to have number of the total charge is going to be the electrons, which is 10 power 21 electrons per meter cube. Here I am talking about meter cube. So typically we don't talk in terms of meter cube, we talk in terms of centimeter cube. So it becomes actually 10 power 16, 10 power 15, right? Because this is 100 centimeter equal to 1 meter. Therefore, it will become 10 power 6. So per centimeter cube, it will become, you will have this much. Okay, so when I substitute with the mass action law, I can calculate what is the P naught. Once I know the P naught, I can tell what is the conductivity due to the majority carrier and the conductivity due to minority carrier. The minority carrier is extremely very small compared to the majority carrier. Therefore, we can very well clearly say the conductivity is primarily due to the majority carrier. That is exactly what it is. With that, I end this lecture. I hope you have understood semiconductors to an extent that is required for a course like devices and circuits. Whatever, with this knowledge, we will move on to PN junction under equilibrium, which means there is no bias applied. Okay, under zero bias, that is under equilibrium. When I bring both P-type and N-type material, what is happening? at the meeting point, at the junction. That we will talk about it. And then under the influence of field, forward bias, which means P connected to a positive terminal of a supply and N connected to the negative terminal. So under the influence of forward bias, what is happening? Under the influence of negative bias, which means reverse bias, what is going to happen? So these things we will see in the class when we deal with the PN junction. Thank you very much. With this, I end today's lecture. If there are any questions, you can post me on my email. I will be happy to answer you either through the email if the answer is very simple. On the other hand, if the answer is requires a meeting, we'll have the meeting. Thank you.